Part 1. What is coal? Coal is a naturally occurring, solid, black or brownish-black sedimentary rock that is primarily composed of carbon along with various other elements such as hydrogen, sulfur, oxygen, and nitrogen. It is one of the most abundant fossil fuels found on Earth and has played a pivotal role in shaping human history, industrial development, and energy production. Part 2. Formation mechanism of coal. Coal is formed from the remains of plants that lived and died millions of years ago in swampy and waterlogged environments. As these plants accumulated in these wetlands, they underwent a process of transformation due to heat and pressure over geological timescales. This process, known as coalification, involves several stages, starting from the initial accumulation of plant material, leading to the eventual formation of different types of coal. 1. Carbon chain lengthening. When these plants die and accumulate, the carbon-rich molecules form the initial basis of coal. Over time, as layers of plant material accumulate, carbon chain lengthening occurs. Simple organic molecules join together, creating longer and more complex carbon chains. 2. Cyclization. During coal formation, cyclic structures can emerge from the rearrangement of carbon atoms. Cyclization involves the formation of rings within the organic molecules. This process can create a diversity of aromatic compounds, contributing to coal's complex chemical makeup. 3. Aromatization. Aromatization is a transformative process where non-aromatic hydrocarbons convert into aromatic compounds, which are characterized by ring structures with alternating double bonds. 4. Removal of functional groups. As organic material undergoes burial and experiences increasing heat and pressure, various functional groups, such as oxygen-containing groups, are gradually removed. The removal of functional groups results in the release of volatile compounds, leading to the enrichment of carbon content in the remaining material. 5. Thermal maturation. Over geological time frames, as sediment accumulates over organic-rich layers, heat and pressure continue to act upon the buried material. This thermal maturation, or coalification, involves a series of complex reactions, including carbonization, dehydration, and dehydrogenation. These reactions drive the expulsion of water, hydrocarbons, and oxygenated compounds, gradually enriching the carbon content. 6. Gradation of coal ranks. The combination of these processes, along with variations in pressure, temperature, and time, results in different coal ranks. There are 4 main types of coal, each characterized by its carbon content, energy density, and properties. Peat. The earliest stage of coal formation, peat is partially decayed plant material with a high moisture content. It has low energy content and is not widely used as a fuel source. Lignite. This is a brownish-black coal with higher carbon content than peat. Lignite has a relatively low energy density and moisture content, making it useful for electricity generation and some industrial processes. Bituminous coal. With a higher carbon content than lignite, bituminous coal is a versatile fuel source. It has a moderate energy density, lower moisture content, and is commonly used for electricity generation, steel production, and heating. Anthracite coal. This is the highest grade coal with the highest carbon content and energy density. Anthracite coal has very low moisture content and burns with a clean flame, making it suitable for residential heating and certain industrial applications. Coal is highly heterogeneous in nature with respect to size and chemical compositions. Coal is fully aromatic in nature. Proximate analysis quantifies moisture, volatile matter, fixed carbon, and ash content, providing insights into combustion behavior. Surface moisture. Surface moisture, also known as free moisture, refers to water that is visibly present on the external surface of the coal particles. It can be easily removed by simple drying methods. Surface moisture does not contribute to the heating value of the coal and is usually driven off at relatively low temperatures. Capillary moisture, also called inherent moisture, is water that is held within the coal's internal pore structure. It's held by capillary forces and is not visible on the coal's surface. This moisture can be partially removed by heating the coal at moderate temperatures. Implications: the presence of different types of moisture in coal affects its properties and utilization. High moisture content can lower the heating value of coal, as energy is required to evaporate the moisture during combustion. Moisture can also impact combustion efficiency, leading to incomplete burning and increased emissions. Moisture content affects coal transportation and storage, as wet coal is heavier and can be prone to spontaneous combustion. Equilibrated moisture. It represents the moisture content the coal holds under specific environmental conditions, reflecting its interaction with the surrounding atmosphere. Importance: accurate assessment. Equilibrated moisture offers a more accurate picture of the coal's moisture content compared to a sample that has not reached equilibrium. This is crucial for understanding the coal's behavior when subjected to various processes. 2. Proper handling. Knowing the equilibrated moisture level helps in making informed decisions about coal storage, transportation, and usage. It prevents unnecessary losses due to incorrect moisture adjustments. 3. Quality control. The equilibrated moisture content directly affects the quality of coal. Consistently high moisture can lead to combustion issues and reduced energy output. 3. Volatile matter. Volatile matter refers to the combustible gases and vapors that are released from coal when it is heated in the absence of air or oxygen. These gases include compounds like hydrogen, methane, carbon monoxide, and volatile hydrocarbons. Importance of volatile matter. Combustion behavior. The volatile matter content influences how easily coal ignites and burns. Coals with higher volatile matter content tend to ignite more readily and produce a higher flame intensity. Flame stability. Volatile matter contributes to the formation of a volatile-rich flame during combustion. This flame helps stabilize the combustion process and contributes to efficient heat transfer. Energy content. Volatile matter contains energy-rich compounds that are released as gases during combustion. This energy contributes to the overall heat output of the coal. Low volatile matter. Coal with a low volatile matter content tends to burn with a longer, more controlled flame and is suitable for applications where controlled combustion is essential. High volatile matter. Coal with a high volatile matter content ignites more quickly and produces a more intense, vibrant flame. 4. Ash content. Ash content refers to the inorganic residue left behind after coal is burned. It consists of minerals, metals, and non-combustible elements present in the coal. When coal undergoes combustion, the organic components burn away, leaving behind the ash. Importance of ash content. 1. Quality assessment. Ash content serves as an indicator of the overall purity and cleanliness of coal. 2. Lower ash content often signifies higher quality coal with fewer impurities. 3. Energy efficiency. The energy derived from burning coal is affected by its ash content. 4. Higher ash content means that a portion of the coal's mass contributes little to the energy output upon combustion. High ash content might lead to clinker formation and slagging in boilers, potentially affecting heat transfer. Coal preparation. Various methods, like coal washing and beneficiation, are employed to reduce ash content and enhance coal quality. Blending. By mixing coals with different ash contents, industries can achieve desired combustion and emission characteristics. 5. Fixed carbon. Fixed carbon refers to the solid, carbonaceous portion of coal that remains after the volatile matter, moisture, and ash have been driven off through heating. It represents the carbon content that contributes to the energy output when coal is burned. Importance of fixed carbon. Energy content. Fixed carbon is a major determinant of coal's energy content. As it is the non-volatile, combustible component, it directly influences the heat produced during combustion. Coals with higher fixed carbon tend to burn more steadily and efficiently. Flame stability. Fixed carbon contributes to the formation of a stable flame during combustion, promoting controlled and consistent burning. 6. Gross calorific value, GCV. It represents the total heat energy released during the combustion process, including the latent heat of vaporization of any moisture present in the fuel. GCV takes into account the heat released from the combustion of fuel and the heat absorbed in evaporating the water content, if any. It is expressed in units like calories per gram, megajoules per kilogram, or British thermal units per pound. Net calorific value, NCV, net calorific value, often referred to as NCV, is a measure of the energy content of a fuel after subtracting the heat energy required to vaporize the water content. NCV is generally considered to be a more practical measure of the energy available for useful work, as it doesn't account for the heat that would be used to convert water into steam during combustion. Difference between GCV and NCV. The key difference between GCV and NCV lies in the consideration of the latent heat of vaporization of water. GCV equals NCV plus latent heat of vaporization of water. Importance of GCV. Energy content. GCV is a crucial parameter for assessing the energy content of a fuel. It quantifies the maximum heat energy that can be obtained from complete combustion. Fuel comparison. GCV allows for direct comparisons between different fuels. Industrial processes. GCV influences the efficiency of combustion processes in power plants, industrial boilers, and other energy-intensive operations. Ultimate analysis determines the elemental composition of coal such as carbon, hydrogen, nitrogen, sulfur, and oxygen content, helping predict its energy yield and environmental impact.